Okay.
I've done that.
That's brilliant. Then I think now is a good time to start. So just before we start, how we usually do it is we don't ask questions during the talk, but all the attendees are invited to type their questions in the chat on Slack. And then at the end, we will read out some questions. And that's the... And of course, you're invited to keep your camera on because that may be a bit nicer for the speaker than just stare into the void. So if they see some faces, that's nice. Okay, but that's all I had to say. Then thank you very much for being here, Ulrike Tillmann, professor at University of Oxford, and her talk is titled Challenges in Persistence Homology and Applications. Thank you very much.
Well, thank you very much. I hope this is going to work. Let me just try out. Oops, this is not going to work. Yeah, that's all right. Okay, excellent. So thank you very much for the invitation, and the Italians amongst you, and congratulations. But today we are going to talk not about football, but topological data analysis. So TDA is a relatively new subject. It is one of these fields where relatively pure mathematics gets applied to various different things in the real world. And I hope to come to some real world applications as well. But I should say right at the beginning that I really am somebody who's have really worked in pure mathematics for most of my life. And this is a relatively new addition to my research. So topological data analysis, why topology in data? Well, in some sense, one can say that data has shape. So clustering is definitely something that people have been doing for a long time. But data, if we think of it as point clouds, it can also come in all sorts of shapes, like here's this Y shape. I come to that particular one in later on, or a circle. And these shapes, if data has this shape, it often matters. So for example, a circle might be some sort of periodic, a sign of periodic cycles in your data and so on. So hence, one wants to go from some data to topological spaces to understand, to study data as topological spaces, because after all, these point clouds as a topological space, they're not very interesting a priori, and they're just discrete sets, and we can't distinguish them yet. So the important thing is therefore to attach some sort of topology to them. And I should say, really in this first few minutes of this talk, I really want to try to give some sort of introduction into topological data analysis and persistent homology per se. Hopefully, maybe some of you have seen it, but hopefully and those who haven't seen it will get some idea of what I'm trying to talk about. So when one goes from these point sets to some sort of topology, well, effectively what one wants to try to do is from this point cloud here, I want to somehow think of it as a shape, as if I enlarge on every point to a little ball. And then the union of these balls is, roughly speaking, intuitively speaking, the shape that we might see. There are, of course, other ways of associating topological spaces, but I'm going to stick with this sort of idea for the talk. So if one does that, then that's very nice, but then one has this huge union, and it seems to be hard to describe itself and what can we do with it. So one actually then reduces this information to combinatorial information. And this combinatorial information are these simplicial complexes. And there are really two types one can associate to such a point cloud, that more of those, but that I want to mention here. And there are two very natural ones, namely the first one is the so-called check complex, where for a given epsilon, a fixed epsilon, we put an edge between any 2 points if there are 2 epsilon apart. And we furthermore put a triangle here if basically the balls that I might see here, this one, and this one centers, they're all intersect. So they're all, these 3 balls of diameter epsilon intersect. And so if they do, I give myself this triangle. And similar with the tetrahedron, if there are 4 points, each, all 4 balls intersect, then I get a tetrahedron, and so on. I can build higher and add higher and higher simplices. And that's one way of building such a simplicial complex. Another way, which has, it's a little bit easier to calculate, is the so-called Vittori-Swipes complex. And it's really just a flag complex on the graph that I see when I build up the check complex. So if K0 are the vertices in my point cloud and K1 are the edges that I get whenever I put them in between 2 points that are at most epsilon apart, then I get a graph on this Vittori-Swipes complex is just a flag complex. So in other words, 3 edges, all of them I can see in a triangle, then I put in the face. 4, I put in a tetrahedron, and so on. So really, these 2 complexes give us similar information, and I mention that in a moment. So why see this is an advantage? Because this combinatorial information now allows me to do linear algebra. So this first line here is the chain complex. And I'm just taking for each of these sets of vertices, edges, and higher dimensional simplices, I take the free vector space generated by these K simplices. And I combine them by defining a map Dn, which gives effectively the boundary. So on the basis element, on an element in Kn, that's an n simplex, I assign to it via Dn the sum of all its faces, Dn-1 faces. I have to be a bit careful about sign, that's why I haven't written actually a formula, but if f is of characteristic 2, maybe has only 2 elements, then this is a well-defined map. And in particular, what I have is that the composite of 2 such maps is always 0, because geometrically, the boundary of a boundary is always empty. Okay. So given this means that the kernel of this map contains the image from the previous one, and the difference is measured by these homology groups. Or really, since I'm working over a field, the only information I can remember is just the dimension of these homology groups, which is the difference between the dimension of the kernel and the image. And there's a nice number. The Euler characteristic can actually be computed via the alternating sum of these Betti numbers. Okay, so these homology groups are catching quite a bit of my topology. And let me just briefly mention why one might like to replace, well, we have replaced the check complex maybe by a Vittori-Swipes complex because it's much easier to compute the whole complex that way. But it's not a big difference between them because the Swipes complex contains the check complex. And as long as our point cloud is from a Euclidean space, then actually the Swipes complex is contained in a check complex for a slightly larger epsilon. On the other hand, I don't want to forget about the check complex because it gives us very good theoretical properties of our homology, namely the check complex, which was just this combinatorial thing. The homology of it is indeed the homology of the underlying space. So we keep both in mind. And persistent homology is now the homology that we get because when we have more than one epsilon around. When you look at data, it's not clear what epsilon might be the right thing to choose. So for example, if I look at this point cloud, you might say, well, maybe roughly this is a circle, so I should expect homology to be equal to 1. But what is the right epsilon to choose? If it is too small, then this looks like a discrete set of things. If it is too big, then it's just one blob. So the idea of persistent homology is really to consider all epsilon between, in a reasonable range. So if I look at the connected components, that's equivalent to looking at H0. What do I get? I get here lots of bars in H0, 1 for every point. And as I move on in my complex, certain bars disappear. They get merged, these two get merged. And finally, I just have one connected component. On the other hand, the first homology here in lilac, I have a spurious one-dimensional cycle somewhere. It's not visible in my picture, but then I have a big cycle, the big one here, and it survives for a certain time until, of course, everything is covered up. And these yellow things are actually the Vittori's Rips complex. Okay, so that's persistent homology. And there are certain things, there are really nice properties about these persistent homology, namely the existence of barcodes, just meaning that indeed I can always represent my homology and in form of picking a basis for the starting one, so that I just get these bars. So every bar is a choice of a basis vector, and so at every epsilon I can just look at how many bars I have, and that tells me the Betti numbers. And that's quite an unusual, it's a theorem that this is possible. It's known as from a representation theory, or just simply that modules over PID have a nice classification. And then the second one is the stability theorem. And the stability theorem really says that if my data set, I change it slightly, so I move these points just a little bit, then indeed also these bars will just move a little bit. So it's a sort of continuity property that one obviously would like to have. To be precise, I need to give the point clouds a metric or topology, and one can do that as a Gromov metric, and I also can give the barcodes metric. Okay, so these are two fundamental theorems, and there have been loads and loads of applications. My favorite one is possibly still the very first one I'm mentioning here by Nicolas Levin and Carlson. And what the application is exactly written in the title, namely topology-based data analysis identifies a subgroup of breast cancers with a unique mutational profile and axonal survival. So it's really quite a stunning application. And I mention a few more in different areas here that have come related to the Center of Topological Data Analysis that I'm associated with. Okay, so this is my very, very quick bird's eye introduction into topological data analysis. And in a way, it would actually be a good moment to maybe to ask questions. I will go into various things in more detail and be more precise in a moment, more mathematical. Are there questions already now?
So one question from the chat is, it seems persistent homology captures the global topological features. Is it possible to extract the topological features locally?
Yes, is the answer. If you're clever, I mean, if you're careful, yes. So it's the same way as, I'm not quite sure whether you're coming from a pure maths background, but if you are, then you can look at local homology. So you can look at and this has been done by some of my colleagues, Vidit Nanda and Heather Harrington and Jared Tanner. So what I've done, and Bernadette Strauss, what I've done is look at the homology in a small radius relative to the homology of an annulus around that. And if you do that, then effectively you can look at local homology. Okay. But it's a good point that in generally you would get global data. Okay, so the next thing I want to do now in this talk is to go through various challenges that topological data analysis and persistent homology faces, and given somewhat of an overview maybe of some of these challenges. So the first one is the inverse problem. In other words, given a data set, and you have the barcode at the end, how unique in some sense is that point cloud? For those of you who have studied of topology and homology theory, of course, you would not expect that to be one-to-one, because even the same way as homology is not a total invariant of the homotopy type, even of a topological space. So, of course, here we have persistent homology, which is a little bit more than just the homology of a space. How much more can you get out of it? So this is really therefore a question about the inverse of the persistent homology. So to be slightly more precise, let me start and fix a simplicial complex K of dimension D. And one way to think of our filtrations that, or complexes that grow is the same way we can think of it as really, I mean, slightly more general even, we can think of filter functions. So in other words, I consider a function f on my simplices, on my set of simplices into R. And then I can filter this complex with respect to the elements in R. Of course, I don't just want any function. I want these functions to observe the inclusion relations between the faces and simplices more generally. So if a face would have to necessarily have function value less or equal to a coface. But if we have this condition, then a filter function gives rise to a filtration of my complex. For technical reasons, I'm going to let the functions just have really values in the unit interval. Now, given such a filter function, so a filtration of my K, that then gives me immediately a way of associating a persistent homology, and hence a barcode. But what is a barcode? Well, the space of barcodes is really, I have bars, finite bars. Those give me elements in R to the 2. And the way I was thinking about it is I have a starting point and an end point. And I also have potentially bars that are infinite. So I just have a starting point, and the end point is really infinity. But of course, bars are not ordered. So I have to mod out by the symmetric group. And furthermore, I want to topologize this space so that I might even have the empty barcode or the bars of length 0 are all identified. So this is this diagonal element, which I just give myself. Effectively, it's also representing the empty bar. And then I need to topologize this appropriately, and there are various ways of doing it. And one popular one is the so-called bottleneck distance. On any subspace, it's more or less a Euclidean distance. Again, I will come back to that later, but it is actually much more complicated. For example, it's not Hausdorff. Okay. On the other hand, we have now our filter functions, and the filter functions, as I said, every filter function gives rise to a filtration of K, and therefore applying homology, I get a persistent homology module and hence a barcode. And I can do this for zero homology up to D's dimensional homology, so I get actually D plus 1 elements in bar. And of course, I can just define this bar K now to be the image of this compact set. And that will have much nicer properties. Anyway, so the question, the inverse question is really, given an element in bar K, what is the pre-image under this persistent homology transform? So here's an example. What are the filter functions? I mean, the example is really the simplest things you can possibly think of is really a unit interval given as a simplicial complex with 3 simplices, namely the singleton, the 0 and 1, and the edge 0, 1. And of course, I have an automorphism group here, namely by Z mod 2, which swaps 0 and 1. And the filter functions, therefore, are giving me a closed 3 simplex. Namely, I get 2, depending on whether I let 0 occur first and then 1, or vice versa. And of course, sigma 3 always has to be less, mapped to something that is greater than sigma 1 or sigma 2. And so here's my simplex. Here's one of them, I guess. And my barcodes, well, each of these simplex is going to be mapped to something. The interior is mapped to something that looks like this. I start with something x, the value of x1, and then I have the value of x sigma 2 and the value of sigma 3, or similar here. And this is my barcode. So these 2 simplices are mapped to this 1 simplex. And I have a further identification, namely on the back of my simplex here. You see, that corresponds to x2 and x3 being equal. But if they are equal, then of course that whole interval is just collapsed. So really, my bar K is now this simplex with identifications. And so the lines here are just going to be mapped to a point. And that's a complete description of my bar K. And that, of course, that has a very nice topology. Okay, so with the student, Jacob Legone, we studied this quite from first principles, and of course the automorphism of the complex are always acting on the fiber. The inverse image of any diagram in my barcodes is a polyhedron complex, and we can also say it's of dimension less than the number of simplices minus the number of endpoints in the barcode over 2. Now, these are very simple observations nearly. Somewhat more interesting maybe is that in this pH is always a map of stratified spaces. And the open strata So this is a map from the filter functions, which is easy to see to be a stratified space. But the barcodes are also stratified, and the open stratas are just given by the automorphisms or the orbits. Sorry, this should be orbits of the automorphisms of the interval. Let me just go back for a moment. How do the automorphisms of the interval act? Well, this ends up in I to the k, so I can just act by an automorphism of the interval. And similar, the barcodes here, these barcodes will basically be not just in general in R, but in I. And I act by an automorphism of I on the barcodes, on the endpoints of the barcodes. So that's very straightforward. Now, we put this as a recent preprint, and what other work has been done in this direction? Well, the closest work has been done by Krianka and Maishekov and Weibel, and they considered literally just a K, but with subdivisions, so not just as an interval that I had just before, but with subdivisions. And they proved that for lower star filtrations, so these are a special type of filtration functions, then actually the fibers are always contractible. And similar Curry, he considered yet a slightly different situation, namely continuous functions on the interval, and that's also each time the fibers are contractible. More generally, Catanzaro, Curry, and various other co-authors looked at certain continuous functions on S2 and tried to analyze this. And finally, possibly most interestingly, Turner, McCurry, and Boyer, they looked at something called a persistent transform. So instead of just having one filter function and looking at its persistent homology and ask, does it sort of specify indeed my source, my shape, my complex, they looked at a whole family of filters and all the barcodes that you could get out of them. And for certain shapes in R3, they proved that if you look now at all these different directions and filters, then indeed the persistent homology can completely determine the shape that you started off with. Okay, so there's a lot of more that one could say. In particular, we compute the example of a triangle, 6 simplices, and it's already quite complicated, over 30 different barcodes and strata, and hence different fibers. And it's not so easy, like it's always contractible, etc. So this is a complicated problem in general. So let me move on now. What about differentiation and vectorization? Now, I guess half of the audience might come from machine learning, and that might be a little bit closer to their heart. What do I mean by differentiation? Well, my filter function, the ones I just had before, of course, were a subset of R to the number of simplices in K, but I might have some sort of map, maybe some sort of parameterization of filter functions from some manifold M. Okay, so we have some parameterization of filters, and we might have also a map from the barcodes to some vector space V, which might be some sort of loss function in the machine learning context, or a vectorization if we want to do some statistics. And there are different ways of defining such a thing. For example, we might want to look at a barcode and ask, well, how far is it from some given barcode, say the empty barcode? So we might try to understand the difference of a given barcode to the empty barcode. Other vectorization methods, there are landscapes and persistence images, which sort of assign to a barcode and in an interesting way a vector space, an element in a vector space. So given now this sort of, we have a parameterization, and then we apply our persistence homology functor, get barcodes, and then we might apply our vectorization or loss function. We get a map from a manifold to a manifold, and certainly that you might hope could be differentiable, right? It has nice structures, and the question can be asked. But furthermore, you can ask the question, in what sense is maybe this first map, or indeed the second map, already differentiable? That, of course, is interesting, this whole pattern, in order to optimize with the choice of a filter function for machine learning, to kind of put in the topology into my learning process. But okay, so we ask now the question for differentiability, for optimization, and maybe just to be a little bit more precise here, what are the situations I might be thinking of? Here's one of them, where I take as my M S2. I have my tetrahedron sort of embedded in R3. And the way I pick now a filter function from my S2 is to say, well, give me a direction in S2, and I'm going to take a simplex, say I take this edge here, and I assign, the filter function assigns to this edge the maximum of this inner product. So wherever x is on this interval, the assignment to this simplex is going to be the maximum in that direction, in the theta direction. Now, and then I say apply first homology. Now, this function actually is going to be differentiable outside these great lines, the green and the blue lines. And that's something that the blue lines, by the way, are sort of the planes that I get, or the great circuits that I get by looking at vectors that are orthogonal to this edge, and this edge. So I get three great circles for those, and the green ones are for the three other edges. And that's actually the general situation. So, I mean, how can I even talk about differentiability? The way to do it is to, well, one way to do it, and certainly, is that we can make these barcodes, they're not manifolds, of course, but we give them a so-called diffeological, the structure of a diffeological space. That's a lot weaker than a manifold, but it's good enough to do differentiation, to make sense out of differentiation. So these maps here to bar, they're just map on these parts here, and then collapse here. There, I call a map into bar differentiable if there is a lift into here, which is differentiable. And similar, a map out of bar into something else will be differentiable if the composition with this map into V is differentiable. And so with this sort of language, one can then say that indeed these maps that we defined before, as long as our parameterization, remember this F is a map from M to the filter function, I of course want that to be differentiable. If that is differentiable, apply pH to it, then this is differentiable on open strata of M. And similar, if I apply any of these loss functions, namely the distance to the zero, to the empty barcode, that's going to be generically differentiable, and similar for some other I didn't yet mention persistent images, but that's another way of vectorizing your barcodes. And indeed, the chain rule holds in this context. So as I said, this open strata we saw here, this example is, so the complement of these lines, we have differentiable maps. Okay, so basically, with some care, these filter functions are therefore learnable in a machine learning setting. Of course, one needs to avoid these boundaries of the stratas, or be careful what one does there. And there are many applications. I just mentioned here one, Jacob and another student, Ambrose Yim, applied this to graph classification. Okay, so then I come to a third really major topic in persistent homology, and that is multi-parameter persistent homology and noise. So noise appears, you know, we have these point clouds, but there might be a lot of noise, either because the reading has been faulty, or measurements have been, or the sample is faulty, and so on. So often there's noise, and then persistent homology does not behave very well, or has sometimes trouble to cope with that. And one way around it is actually going to so-called multi-parameter persistence. So let me give you an example. So we might have sampled here points from two rings, a smaller and a bigger one. But as you see, we have lots of false positives. And if you just did straight persistent homology on this, I would be in trouble. On the other hand, if I use a second parameter, namely co-density, as a second filtration, then I can get around these problems a little bit. So I can measure the density by, for example, the inverse of the closest, the fifth closest other point, neighbor, or something like that. So one can think of some sort of density function, and here the density is actually indicated by the intenseness of the green. So these points are not dense and they're very light, while these points are quite dense and so dark. Now the filtration, you know, the Vittorius-Rips rotation takes the distances into account. But I also now want to have the second parameter that takes into account the density. And so really, I get a filtration that's really, yeah, a two-dimensional, taking both of these things into account. So in general, I have a multi-parameter persistent module. It is really, I can think of it as a functor from the ordered category of vectors in Rn, ordered by lexicographically, basically. And it's a functor into vector spaces. And so whenever the vector A is less than the vector B, lexicographically, then I expect a map of linear maps. And that's exactly what I get when I do this for persistent homology. Namely, I have my two, I guess in this case, two parameters, density and length. And with those fixed, each two length and density fixed, it defines for me a subcomplex of the Vittorius-Rips complex. And hence I can apply homology to this subcomplex, and I get a whole persistent, two-dimensional persistent homology module from this process. Now, these persistence, multi-parameter persistence modules are much harder theoretically. Indeed, there is a distance function well defined on these, and it's going to be actually, the interleaving distance is actually NP hard, so extremely hard to compute. Stability holds, which is good. But on the other hand, there's no analog of something like a barcode. And these modules, from representation theory, a way of saying this is that they're not finite. Sorry, they're not finite and type. And means that I can't just decompose these in some sort of interval modules. So there's been a lot of work on these as well, starting with Carlson Zamorodian. Some are more application-oriented, some are computationally oriented. We have tried to do something applying algebraic geometry. But what I really want to talk about next is really an application, namely, well, just because you can't find an invariant that's very nice computable everywhere, and it's an invariant that is actually discriminative, that doesn't mean I can't get some information, some useful information out of these multi-persistent homology modules. And indeed, the first very useful measurement are these rank invariants. Namely, if I have two vectors, so two elements in Rn, S and T, then the rank invariant between these two is given by the dimension of the vector space at S, and then mapping to the vector space at S plus T. And indeed, in one dimension, if I knew all these rank invariants, I would know the whole module. But again, of course, in higher dimension, that's not the case. Now, the persistence landscape, I mentioned them before as a vectorization method, and that was actually defined first by Bubenik, and a student in Oxford, Oliver Weipont, has actually generalized this to multi-parameter persistence landscapes. And the way it's defined is that it's really a function. So these are, being a function in particular, it is a vector space. And the way we define them is that for a given k, we look at the soup of all the epsilon. So that's the rank. So I'm looking really locally at x, but I go a little bit before x and a little bit after x, and want the rank of the persistent homology, the stuff that survives from x minus a little bit to x plus a little bit. I want the rank of the module to be greater equal to k. Now, these, again, these persistent landscapes are actually completely describing the persistent module in dimension 1. However, in these higher dimension, and the information they're going to recover is effectively the rank invariant. So it's not a complete invariant. However, they are very useful. They are, in particular, vectorization. They are stable again. They satisfy the strong law of large numbers, statistics and central limit theorem. So in particular, it means we can talk about confidence intervals, and they approximate normal distributions if we take large enough samples. So there's some very good theoretical, satisfy some very good theoretical properties, and we now can apply them to some real life problems. So, oops. Yeah, sorry, actually, this is an illustration of what I just said. So we had these rings and the two-dimensional persistence. Sorry, two-dimensional persistence module. And indeed, here is another one with 3 rings, and here are the 2 the landscapes associated to these. So this one here, I'm looking at H1, and this is when K is 1. You know, can I cover those rings? And the answer is yes. This one will show up quite early already. This down here is the co-density, and up here is the radius. Co-density being, well, relatively survives relatively long. The radius doesn't have to be big, and I do actually see this first ring. With the second one, I need to have a little bit more co-density, but in particular, I have a higher radius, and I see this second ring showing up here again for k equal to 1, and not much for k equal to 2 and k equal to 3. On the other hand, these 3 rings show up in a slightly different way, because they all should survive they all have the same radius, and that's showing up here that when lambda is equal to 1, the k is equal to 1, then I have here my co-density in radius, and here it's my ring showing up. But of course, I have 3 rings, so I have more or less the same sort of shape for the same region of co-density and radius for all these 3, because they're roughly the same size. Okay, so that's just illustrating how these landscapes can be read. And I now want to do the application. It's an application actually to immune cell tumors, so patterns of immune cells in tumors. So I said that, well, I want to do 2 things. One is, the first thing is to sort of illustrate maybe that multiple persistence can cope with noise better than single persistent. And here we have actually a tumor, and the green cells from the outside are actually immune cells, and with some chemical help, they infiltrate over time the tumor. So as time goes on, of course, the persistence homology should have a big ring here, H1, and we should see less and less. This is the same panel, same simulation, only that we have false readings, which are clinically actually quite happen quite often and have to be taken account for. And these are just actually models that were developed in Oxford by my colleagues. And so here we have the ones with noise. And now we have down here the 2 panels. This right one is a panel where we just apply persistent homology straightforwardly. And these different curves correspond to basically how much chemical help these immune cells have received in order to go into the tumor, how quick they are. And indeed, it's very difficult to actually make much out of these, and the signals are not very strong. While when we do the same thing with multi-persistence, so where we take the density of the cells into account, of these immune cells, then we get a much stronger signal and a much more coherent dying off at the end. And even the, how much chemicals are given at each stage for each trial is visible, and the top one being the slowest with no help at all. Okay, so that's just a small illustration that actually the multi-parameter persistence is helpful in this very concrete setting to give us a stronger signal than single persistence. And then let me go to this is actually my last slide, and go to this panel This is sort of much more exciting from an application point of view, namely, and I should say my biological colleagues are much more excited about this, because what we have been able to show or expect, and the data is really not, we don't have enough good samples yet to do that, but it's indicative that actually one possibly can just use this radius co-density filtration and analysis instead of radius hypoxia analysis. So hypoxia means the absence of oxygen, and the oxygen level, of course, is important for the tumor and the cells, but it's very difficult to measure, and in general, one prefers to do things, of course, mechanically. And it looks like the co-density might be potentially be a good proxy for hypoxia. And let me just very quickly talk you through these pictures to give an idea. So the picture panel A up here is actually a photo of real tissue. Then in panel B, there are 3 types of immune cells, CD8, FOXP3, and CD68. And each of these have different densities. And the densities are, while blue is dense and red and yellow is less and less dense. And so we have these filtrations. And then for each of these, one can try to either use the hypoxia and the radius, the spatial distances, to come up with a 2-dimensional filtration of our point cloud, or one just uses this with the co-density function. And that's giving us a panel like this. So C, I don't even know which one it is, whether it's the CD8, the FOX, or the CD68, but it's a sample of how we would get filtrations, 2-dimensional filtrations of these point clouds using co-density here and hypoxia here. And then one can compare the outcome, the landscapes. One can integrate the and try to, repeating, when actually these point clouds are too big, one has to therefore take subsamples, etc. And taking subsamples, one does the statistics on this and comes up with panel D down here, which shows that for the CD8, for example, we have, there's a strong, our H1, the integration of our first landscape ends up with the distribution here. And you can compare that with the radius hypoxia results. And similar here for this FOXP3, this is the radius co-density. One gets this graph, and here we get this butterfly diagram. And similar with the CD68. And roughly speaking, these sort of agree. And that's, I think, got my biological and medical colleagues who are working on this together very excited indeed. So I leave you with that, and thank you very much for listening.
Thank you very much for the great talk. Let's thank our speaker. Thank you, that was great. And there are some questions, many questions in the chat. So I will forward some of those. The first question, do the properties presented under the hypothesis of using the bottleneck distance between barcodes hold for other distances, such as the Wasserstein 1 or Wasserstein 2 distances that might be more friendly for machine learning?
So the continuity, I think, works for all Wasserstein distances. Is that right? Now I have. I think that's true. I have to think about that. I mean, that's the main one I'm using here. I'm sorry, I have to think about the definition now. Isn't that something that might actually follow? No, I have to be careful. So it's true in the settings that I have considered, because there I have considered always a fixed simplicial complex and restricted myself to that. And because I'm restricting myself to that, the differences are not going to be showing up. So, yeah.
So the answer would be?
In general, I'm not 100% sure. In the cases I am looking at, yes.
Yes. Okay, thank you. Then there is a second question. Can we use the topological information on barcodes or persistence diagrams to recover a fixed epsilon that captures an approximation of the structure of our point cloud?
So in a fixed, if you have the barcodes, then I'm not sure I have completely taken this in. If you have a barcode and you see the whole thing, then you should be able to find an epsilon at which, you know, to say this is an interesting epsilon to look at. So for example, here, because this, you know, there's a short bar, you might think, well, maybe that's not actually catching what I really want to catch, but this bigger bar, there seems to be something significant about this. And if I take this epsilon in the middle, like 1.6, then indeed I see this circular shape. If I understood the question correctly.
Yes, yes, I think that's a great answer. Yes, thank you very much. And so we don't have a lot of time, but I'll ask one more question, and that is, how does the reliability or sensitivity of this barcode-based description of the geometry of the point cloud change when increasing the dimension of the space in which the points are embedded?
Okay. So first of all, if I just increase the, I mean, if I include one point cloud into a bigger space, then nothing happens. But that's not, I think, the question. Sorry, could you start from the beginning?
Okay, so I'll read it out again. How does the reliability of this barcode-based description change when increasing the dimension of the space in which the points are embedded? So I would imagine you don't just include R2 in R3, but maybe you make some error when including it.
Well, if you make errors, then of course each error introduces some problem. But if the question is, you know, do I worry about? I mean, as long as the distances are preserved, then nothing will change. I can consider myself in an arbitrary background space, so that's not a problem. So yeah. The dimension per se, the background dimension per se is not, there's no problem there. I just need to be able to compute. So possibly what this is about, it's just general sparseness. And I did actually originally include this as a sort of as a problem. And I think that might, you have to worry there, and that will change, namely when you look for null models, right? So you have some point cloud and you wonder, you know, what sort of homology should I expect at what epsilon? And that is a great question in itself, and in some sense a big subject area. And one way to try to attack or get some feeling for this is people have studied random geometric complexes in that context, and ask themselves, you know, if I have some point cloud in, say, well, let's say a compact D manifold, right? At what point, at what radius, and what density do I expect to recover the homology of the manifold? And there are perfectly good studies and reasonable answers to that, at least asymptotically, right? As the radius gets smaller and smaller, but maybe with that, the density gets larger and larger.
Yes, that makes sense. Thank you very much. And okay, so it is already past 5. I think we leave it at that. So thank you again very much for the talk. That was great. And we'll be back here with the next talk at 6 p.m. So we take a break now, and we'll all see you again in the same Zoom room in an hour. So yeah, thanks very much for being here. Oh, we can stop the recording now as well.